In this video, we shall study what is log x and what is ln x. Over here, log x means to the base 10 and over here the base is e. You can take any base over here, right? But when we generally say, when you see on the calculator log, it uses the base 10, means I am talking about this. Our number system is based on powers of 10, right? Decimal system. We use decimal system. The button ln uses base e, that is 2.71828. These are sometimes called natural logarithm. These are called natural logarithm because of special properties of the number represented by e as when used in exponential functions. So log means you will take base 10 and ln means natural log to the base e. Now, if I say that I have to take natural log of x, that means I have to take log of x to the base e. Ln x equals to log of x to the base e, and what is the relation between them? Ln x and log, natural log and log. This can be written as, ln x can be written as log of x to the base upon log of 2.71828, and base can be anything, but the base over here and the base over here must be same. We are generally taking 10. I hope this is clear, children. Now, for graph, we will be considering natural log and log of x to the base e. This is the inverse function of exponential function. This is the log function, this is exponential function, and they are inverse of each other. Suppose I have y equals to e raised to power x. So this will be inverse of this function and it will be y equals to ln x. Okay, children? Ln x or log x is the inverse function of e raised to power x. E raised to power x and its inverse function is ln x. Okay, and this is the diagram. This is e raised to power x exponential function, and this is its inverse, that is the logarithm function. The blue graph is y equals to e raised to power x, and the green graph is y equals to log of x to the base e, also known as ln x. Instead of writing log of x to the base e, I can directly write natural log of x. These are inverse and are similar to the graph you saw earlier at the beginning of section 2.2. One feature to notice about y equals to e raised to power x is that as x increases, not only does e raised to power x increases, but its rate also increases. The gradient of the graph gets larger. You have studied this. Now use your calculator to find the values of log 16 to the base 10. Now always, before doing this, always remember that 1 has logarithm 0 in any base. Means if you take log of 1 to the base anything, you will get 0, because when you send it over here, anything raised to power 0 equals to 1. The numbers below 1 will have negative logarithm. Over here you can see this and this. The answer would be negative. anything between 1 and base will have positive logarithm. Less than 1 means, suppose I am taking log of 5 to the base 10, I will get this as a positive logarithm less than 1. You can see it over here that I have 2. That is log of 2 to the base e. Value of e is 2.7 something, right? So, and this 2 is between 1 and 2.7, that is e. That is e. So, value would be less than 1. Okay, it will be negative for values less than 1. Okay, children, keep this in your mind. Again, use your calculator. Log of 7 to the base 10 and log of 4 to the base 10. You can directly write this as log of 7 upon 4 to the base 10. This is 4. Okay. Same thing can be done over here also. Over here also. Let us study an example. An earthquake of magnitude 3.0 on Richter scale releases the energy equivalent to 480 kg of TNT. If the earthquake is of magnitude 3, it will release an energy of 480 kg of TNT. How much energy will be released by an earthquake of the following magnitude: 3.2, 4.0 and 7.5? Study this carefully. An increase of 0.2 on Richter scale roughly doubles the amount of energy released by an earthquake. Even if it increases by 0.2 amount, it doubles the energy. So, an increase of 1 gives a multiplying factor of 31.7. That is very close to 2 raised to power 5. You can use 2 raised to power 5 also over here. So, using this information, we can define a relation as 0.48. This must be taken in tons. This must be taken in tons into 31.7. Why 31.7? Suppose if I increase it by 1, it gives a multiplying factor of 31.7. Okay, raised to power something. Suppose I have an earthquake of 3.2. So how much is the increase? The increase is 0.2. The increase is 0.2. Here we will have the increased quantity 0.2, and the answer would be approximately 1 ton of TNT. Now here the increase is from 3 to 4, right? From 3 to 4. 3 to 4. So increase is 1. So I will substitute 1 over here. And I will get the answer as 15 tons of TNT. Over here 7.5. There is an increase of 4.5. So I will substitute 0.48 into 31.7 raised to power 4/5. And that will release the energy approximately equal to 2.7 million tons of TNT. A radioactive isotope has a half-life of 20 days. Initially, it has a mass of 60 grams. How much will there be left after 20 days? And this means that the radioactive, suppose I am having this much radioactive substance. In 20 days, it decays and becomes half of it. That is, only half part is left. And the other part gets decayed. Initially, the mass is 60 grams. How much will there be after 20 days and 30 days? See children, the half-life is the length of the time it will take for the mass to decay in half. That is the half amount of the mass is decayed. This is the full amount and the time taken for it for the half amount to decay, for this much part to decay. The first part is very clear. A radioactive isotope has a half-life of 20 days, means in 20 days it decreases to half. If the initial amount is 60, after 20 days it will become 30 grams, becomes half. See, this question can be converted into mathematical form, right? That if initial mass of the substance is 60 grams, so after first half-life period, it will become half. Again, after second half-life period, it will again become half of the remaining part. After third half-life period, it will again become half, and so on. Okay children, here we have 20 days and half-life is 20 days, right? So how many half-life periods? Only one half-life period. So 60 into half raised to power 1. 60 into half raised to power 1. That will give us 30 grams. So how much mass will be left? 30 grams of mass would be left. And over here we have 30 days. So 30 days means how many half-life period? One half-life and days. So one half-life is 20 days. So 30 days would be how many half-life? You can find it, and that will be 3 by 2. That is 1.5 half-lives. 1.5 half-lives. And we can use this relation. 60 into half raised to power number of half-lives. 60 into half raised to power 1.5, and that will give us 21.2 grams. I hope this is clear, children. I am giving you some questions for homework. Exercise 2.3, question number 1, 2, 3, and remaining part of 3 is B over here, and 4. Okay children. That's all for today. Thank you very much.